Kirchhoff's voltage law is one of the cornerstones of circuit analysis. We apply it almost automatically. The algebraic sum of voltages around any closed loop is zero. But that statement comes with an assumption, one that's often left unstated, and once that assumption breaks down, so does KVL. Imagine connecting two voltmeters across the same 2 points in a circuit, the exact same 2 points. Should they read the same voltage? A lot of people would instinctively say yes. After all, voltage is the potential difference between 2 points, isn't it? Yet, in one of the most well-known lectures from MIT's Electricity and Magnetism course, Professor Walter Lewin performs an experiment in which the two meters report different voltages.
I attach a voltmeter here. That voltmeter will show me plus 0.9 volts. Now I attach a voltmeter here. The same one. I flip it over. It's connected between point D and point A. It will read minus 0.1 volt.
From this, he argues that Kirchhoff's voltage law is not a fundamental law at all, but rather a special case of Faraday's law, one that breaks down in the presence of a time-varying magnetic field.
Faraday has no problem with that. Kirchhoff has a problem with that. But who cares about Kirchhoff? Faraday is the law that matters, because Faraday's law always holds. Because if the phi dt is zero, then you get Kirchhoff's. Kirchhoff's rule is simply a special case of Faraday's law. And Faraday's law always holds. So Kirchhoff is for the birds, and Faraday is not.
Years later, electrical engineer Mahdi Sadaghdar, better known as ElectroBOOM, challenged that conclusion.
I repeated the same test and I agreed with his measurements but not his conclusions.
According to him, KVL never actually fails. The experiment is real, the measurements are real, but the interpretation is wrong.
So the entire reason Dr. Lewin was reading two different voltages was due to bad probing. My conclusion? Kirchhoff laws hold and have held nicely for me so far.
So who's right? More importantly, what does it actually mean for voltage to depend on the path you take? Answering that question takes us well beyond circuit theory. We'll need to understand the difference between conservative and non-conservative electric fields, why electric potential exists in some situations but not in others, and how Maxwell's equations determines when Kirchhoff's laws can and cannot be applied. Along the way, we'll recreate Dr. Lewin's experiment using a full electromagnetic simulation, develop an equivalent lumped element model, verify it with a SPICE, and examine exactly where the two arguments agree, where they diverge, and what assumptions each side is really making. By the end of this video, my goal isn't simply to decide who won an internet debate, it's to understand why the debate exists in the first place. And in doing so, develop a much deeper intuition for voltage, Faraday's law, and the remarkable way Maxwell's equations connect field theory with circuit theory. Before we dive into the core of the topic, let's take a quick refresher on some foundational ideas on electrostatics, just to make sure we're all on the same page. Let's start with Coulomb's law. This is the basic rule that tells us how two charged objects interact. It says that the electric force between 2-point charges is directly proportional to the product of their charges, and inversely proportional to the square of the distance between them. In simple terms, the bigger the charge is, the stronger the force, and the farther apart they are, the weaker the force. Like charges repel, opposites attract. To isolate the effect of the source charge, we define the electric field as the force per unit charge experienced by a test charge Q2. The actual force in a test charge is then F equals E times Q2. Charges create stresses on the space around them called an electric field. and this field interact with other charges, causing an electric force. As you can see, there is no other charge present, only a single charge sitting here. However, even though there is no second charge, there is already a potential force at every point in space surrounding it. In other words, space itself is stressed due to the presence of this charge. This stress in the space doesn't result in any actual force until another charge is introduced. But the moment you place a second charge into this region, it immediately experiences a force. It gets a kick. This reaction is governed by Coulomb's law, which describes how the electric charges interact through the electric field created by other charges. There is only a single charge located here. No other charges are present. However, the space around this charge is not empty in terms of physical influence. The electric field created by the charge causes a kind of tension throughout the space, meaning there's a potential force at every point. The entire region around the charge is essentially stressed due to the presence of the charge. The moment a second charge is introduced, this field interacts with it immediately, exerting a force. A strong push or pull depending on the nature of the new charge. In essence, space is primed and ready to act. It just needs something to act on. If the source charge is positive, the electric field points away from it. If the source charge is negative, the electric field points toward it. A positive discharge moves in the direction of the electric field. A negative discharge moves opposite to the direction of the electric field. An electric field describes the influence a charge exerts on the space around it. You can think of it as an invisible force field that surrounds the charge. When another charge enters this field, it experiences a force. The electric field E is defined as the force per unit charge. It is a vector quantity, meaning it has both magnitude and direction. Work is done when the force causes an object to move. In the case of a charged particle in an electric field created by another charge, the field applies a force in the particle. If the particle moves, the work done by the field depends only on the component of motion that is in the direction of the field. Any motion that is perpendicular to the field does not contribute to the work. This is because work is defined as the dot product of force and displacement. The dot product measures how much of the displacement aligns with the force. If the displacement is perpendicular to the force, their dot product is 0 and no work is done. Work done on an object typically results in a change in its kinetic energy. We'll see later in more detail that the electrostatic electric field is conservative. This simply means that the total mechanical energy, kinetic plus potential, stays constant. So if the potential energy changes, the kinetic energy changes by the same amount in the opposite direction. When work is done by the electric field, the particle's kinetic energy increases, meaning it speeds up and moves faster. Since the total mechanical energy is conserved in electrostatics, this increase in kinetic energy must come from a decrease in electric potential energy. In other words, work is the minus change of electric potential energy. Electric potential energy is the energy a charge has because of its position in a conservative electric field. Just like how lifting a book increases its gravitational potential energy, moving a charge within an electric field changes its electric potential energy. From there we get to electric potential, which is often just called potential, the potential energy per unit charge. So instead of talking about how much energy a particular charge has, we talk about how much potential energy any charge would have at a specific point in space. Potential is measured in volts. So the change of potential, or the potential difference, is the change of potential energy per unit charge. We have an expression for change of potential energy, F times L. Force per unit charge is the electric field, so potential difference is E times L. If a particle moves along a curved, or let's say non-linear path in the presence of electric field, we can still calculate the total work done by the field. That is the potential difference. To do this, we evaluate the electric field at each point along the path and take the dot product of the electric field vector E with small displacement vector dl pointing in the direction of that path. By summing the contributions of work done over all these infinitesimal segments, we obtain the total work. And in a limit, as these displacements becomes vanishingly small, this summation turns into an integral. Electric potential difference equals the integral of E dot dl. This captures the total work done per unit charge as we move along the path. Here E is the electric field vector and dl is a tiny step, a differential element along the path we're integrating over. Potential difference between 2 points is also called voltage, the amount of work needed to move a unit charge from one point to another in an electric field. If the electric field is conservative, the voltage between 2 points depends only on their positions, not on the path taken to get from one to the other. In contrast, in a non-conservative field, the voltage does depend on the path. So with that in mind, let's now dive into the difference between conservative and non-conservative fields. Let me revisit some concepts from vector calculus just to lay the groundwork before we go deeper into the nature of these fields. Suppose we have a function of x and y. The partial derivative with respect to x tells us how fast the function changes as we take a tiny step in the x direction. Likewise, the partial with respect to y tells us the rate of change as we move a little in the y direction. And the same idea extends to the z direction if we're working in 3D. Putting all of these together gives us the gradient vector, a vector that points in the direction of greatest increase of the function. When you have a function with more than one input like v of x, y, and z, the gradient tells you two key things: how fast the function is changing and in what direction it's increasing the fastest. This all comes from partial derivatives, which measures how the function changes as each individual variable changes on its own. So the gradient of a scalar-valued multivariable function is a vector field. That vector field points in the direction of the steepest increase of the function, and its magnitude tells you how steep that increase actually is. For example, consider a scalar function v of x, y, and z. The gradient of v points in the direction of the maximum rate of increase of the function, and the magnitude tells you the rate of increase, essentially the slope in that direction. Now, suppose we take a tiny step in 3D space, represented by the displacement vector dl. This vector captures both the direction and distance of that small move through space. The dot product of them gives the total differential dv, which tells us how much the value of v changes as we move an infinitesimal distance dl through space. A multivariable function can be visualized using contour lines, which represent sets of points where the function has the same output value, also called the z-value. These lines effectively illustrate the height or the level of the function across a plane, like tracing elevation lines on a topographic map. An important property of the gradient vector is that it's always perpendicular or orthogonal to the contour lines. This happens because the gradient points in the direction of the steepest increase of the function. In contrast, when you move along a contour line, the function's value stays the same. There is no increase or decrease, so the only direction where the function can increase most rapidly must be at a right angle to the contour line. Suppose we have a function of a single variable f of x. The derivative of this function with respect to x tells us how rapidly f of x changes as x changes. Meaning if we increase x by a very small amount dx, then the function changes by an amount df. The derivative df dx represents the ratio of this change. It's a factor that relates a tiny change in x to the corresponding change in f of x. The fundamental theorem of calculus tells you that if you have a function f of x whose derivative is df dx, then integrating that derivative brings you right back to the original function. We saw that df is the infinitesimal change in f when you go from x to x plus dx. The fundamental theorem of calculus states that if we divide the interval a to b into many small segments of width dx and sum the corresponding infinitesimal changes df's over each segment, the total sum gives the net change in the function f over that interval. In essence, the accumulation of all those tiny changes, the df's, across the interval a to b results in the overall change in the function's value from f of a to f of b. In other words, there are two ways to determine the total change in a function. You can subtract the function's value at the starting point from its value at the end point, or you can add up all the tiny changes, the df's, along the way. Both approaches lead to the same result. Suppose we have a scalar function of three variables, v of x, y, and z. If we start at point A and take a small step dl1, the function v changes by an amount approximately given by the direction derivative of v along dl1. Here del v is the gradient of v and dl1 is the tiny displacement from point A. Now we take another step dl2 and the function changes again, this time by del v dot dl2. And as we continue along the path from A to B, advancing through a series of these infinitesimal displacements, we keep evaluating the gradient at each point and taking its dot product with the tiny step dl. Each of these gives us the incremental change of v at that location. So the total change in v as we move from A to B along the path is the integral of del v dot dl from point A to B. This is known as the fundamental theorem for gradients. Much like the original fundamental theorem of calculus, it tells us that the line integral of the gradient of a function equals the difference in the function's values at the endpoints. If you examine this closely, you will notice that the expression inside the integral is a dot product of a vector field with a differential displacement vector dl. But here's the key point. This theorem only applies when the vector field in question is actually the gradient of a scalar function. If the vector field is not a gradient field, that is, if it doesn't come from the gradient of some scalar function, then the theorem simply does not apply. In fact, not all vector fields are gradients of functions. Those that are vector fields that can be written as the gradient of some scalar function are called conservative vector fields. The others, the non-conservative vector fields, don't come from the gradient of any scalar potential function at all. They might still have structure, but they lack this special property of being tied to a potential. A vector field E is said to be conservative if there exists a scalar potential function V such that E equal minus del V. In other words, a conservative vector field is one that can be expressed as the negative gradient of some scalar function. This minus sign reflects that the field points in the direction of decreasing potential. Determining whether a vector field is conservative often involves checking whether its curl is zero. But the situation is a bit more nuanced than it might first appear. A zero curl is a necessary condition for conservativeness, but it's simply sufficient if the field is defined over a region that is simply connected, meaning roughly a space without any holes or gaps where loops can sneak through without being shrinkable to a point. If the curl of a vector field is not zero, then the field is definitely not conservative. This is a straightforward and reliable test. Non-zero curl rules out the possibility of the field being the gradient of any scalar function. If the curl is zero, we cannot automatically conclude that the field is conservative. This depends on the nature of the domain where the vector is defined. If the domain is simply connected and the curl of the vector field is zero, then the field is conservative. But if the domain is not simply connected, even if the curl is zero, we can't be sure. The vector field might be conservative, but it might not. We'll define simply connected more precisely in the appendix, but intuitively it means the domain has no holes. Any loop within the domain can be continuously shrunk down to a point without ever leaving the domain. In most cases, especially in electromagnetics textbooks and typical applications, the domains we work with are relatively straightforward and are assumed to be simply connected. In these kinds of nice enough domains, checking whether the curl is zero is often sufficient to conclude that the vector field is conservative and that it represents the gradient of a scalar function. Let's take a look at some examples. First, here's a conservative vector field. This field is the gradient of a scalar potential function. To visualize this more clearly, I'll plot both the vector field and its potential surface on the same axes. Instead of a 3D surface, we can also represent the potential function using contour lines. Each contour corresponds to a constant value of the potential, essentially a height on the surface. Now, here's another example of a conservative vector field and its corresponding potential function. Again, notice how the vectors align with the gradient of the potential, pointing in the direction of steepest ascent. Next, let's look at a non-conservative vector field. Unlike the previous examples, this field is not the gradient of any scalar function. That means there is no single valued potential function associated with it. Here's another non-conservative vector field. Notice something important. The vectors here exhibit a rotational component. This kind of swirling behavior indicates that the curl of the field is not zero, a key characteristic of non-conservative fields. Now let's get back to the fundamental theorem of gradients. If a vector field E is the gradient of a scalar function V, then a line integral of E over a curve C from point A to point B depends only on the values of V at these endpoints. It doesn't depend on the path taken, just where you start and where you end. We can't just arbitrarily assign any vector field in this context. We specifically need a field that comes from the gradient of a scalar function. But here's the catch. Not every vector field can be written this way. For example, magnetic fields are fundamentally non-conservative. They have rotational structure, and as a result, they cannot be expressed as the gradient of any scalar function. In the language of electromagnetics, this distinction becomes particularly important. Not all electric fields arise from the gradient of a scalar potential. For example, induced electric fields, those generated by a changing magnetic field, as described by Faraday's law, are non-conservative. And because of that, they cannot be represented as the gradient of any scalar function. These fields have curl, they loop around, and their behavior is fundamentally different from electrostatic fields. In the context of electric fields, let us consider a simply connected domain, which, as we've noticed, is a common and practical assumption in most physical situations. Now, if an electric field E has zero curl, or equivalently, if the line integral of E around any closed loop is zero, then the field is said to be conservative. In this case, the electric field can be expressed as the negative gradient of a scalar potential function. This scalar function V is known as the electric potential, or more commonly, voltage. It assigns a potential value to every point in space where the field exists, meaning the voltage is defined pointwise throughout the domain. The line integral of the electric field from point A to point B gives the potential difference, or the voltage, between those 2 points. Since V is defined at each point, this potential difference depends only on the values of V at the endpoints and is independent of the path taken between them. On the other hand, if the electric field has non-zero curl, or if the line integral around a closed loop is not zero, then the field is non-conservative. This kind of field typically arises in time-varying magnetic fields as described by Faraday's law. In a non-conservative field, there is no scalar potential function whose gradient equals the electric field. That means a unique voltage function cannot be defined across the domain. Since voltage isn't well defined in this context, to compute the potential difference between 2 points, you must perform a line integral of the electric field along a specific path. And in this case, the result depends on the path taken, not just the endpoints. So there can be infinitely many possible values for the potential difference between 2 points, depending on the path of integration through the field. Let's use a visual example to better understand the difference between conservative and non-conservative fields. Suppose we have a conservative electric field. Such a field can be expressed as the gradient of a potential function, often referred to as electric potential, or simply voltage. Now imagine a set of contour lines representing curves of constant potential. At every point, the electric field is perpendicular to these contour lines. That's because the field always points in a direction where the potential increases most rapidly. In a sense, it's trying to reach the next contour line as quickly as possible. If we integrate the electric field from point A to point B along a certain path L, we'll get the voltage difference between those 2 points. Let's take a closer look at the expression inside this integral. The path from point A to point B is divided into infinitesimal segments, each of length dl. At each segment, the electric field E makes an angle theta with the direction of the path. The term E cosine theta gives the tangential component of the electric field, the part that's aligned with the direction of motion along that tiny step. This component is what actually contributes to the work done by the field. At the first segment, we get a certain tangential component of the electric field, how much of the field points along that tiny bit of the path. As we move to the next segment, this component might change, and it keeps changing from one segment to the next. In the middle region, the electric field is nearly perpendicular to the direction of the path. Therefore, E cosine theta is equal to 0. This means the tangential component of the electric field is 0. and the field does negligible work along this part of the path. This variation captures how the electric field aligns with the direction of the path at every point. So, as we proceed from point A to point B, we're effectively tracing out a curve that represents the tangential component of the electric field along the entire path. And when we integrate along that path, we're summing up all of these aligned contributions, which gives us the total potential difference between the 2 points. As we move along the path from point A to point B, the curve represents E cosine theta, which is the tangential component of the electric field along that path. At every tiny segment of the path, which we call dl, the small contribution to the line integral is the dot product of E cosine theta and dl. This quantity represents the infinitesimal work done per unit charge by the electric field over that small segment of the path. In other words, it measures how much the electric field helps move a unit charge forward along that tiny step. Now, if you add up all these tiny contributions along the entire path from A to B, we get the total shaded area under the curve. This area represents the line integral of the dot product of E cosine theta and dl from A to B. Physically, this quantity tells us the work done per unit charge by the electric field as the charge moves from point A to point B. And because the electric field is conservative, this work per unit charge is exactly equal to the potential difference between A and B. If we consider different paths between points A and B within the same conservative electric field, each path will generally yield a different curve when we plot the tangential component of the electric field along that path. That's because the direction and orientation of each infinitesimal segment vary from one path to another, which affects the value of E cosine theta at each point. Once again, E cosine theta is the component of the electric field aligned with the path. So, while the shape of the tangential component curve changes depending on the path, something remarkable stays the same. The total area under each of these curves, that is, the line integral, remains constant. This is a defining feature of conservative fields. The work done by the field is path-independent, even though the individual contributions along different paths may vary. The voltage difference is equal to the potential at point A minus the potential at point B. That is the value of the contour line at point A minus the value of the contour line at point B. If we move along a closed path, starting at point A and eventually returning to the same point, then at each infinitesimal segment, we can still evaluate the tangential component of the electric field. Together, these values form a curve that shows how the tangential field behaves along the loop. But here's the key. The area under this curve is 0, and if we move along different closed paths, we may get different curves. But the total area under each, or the line integral, is still 0. In other words, the line integral of a conservative electric field around any closed loop is always 0. This reflects a fundamental property of conservative fields. They have no net circulation around the closed path. And that's intuitive, because when we go all the way around and come back to where we started, we've returned to the same contour line. So the value at point A minus the value at point A is 0. But this is not true for non-conservative fields. In those cases, moving along a closed path can result in a non-zero line integral, indicating the presence of circulation or rotational behavior in the field. If we consider different paths between points A and B within a non-conservative field, each path, just like before, will yield a different curve when we plot the tangential component of the field along that path. As in a conservative case, The direction and orientation of each infinitesimal segment vary, which affects the value of E cosine theta at every point along the way. But here's the crucial difference. In a non-conservative field, the total line integral of the field from point A to B depends on the path you take. That means the area under each tangential component curve, which represents the accumulated work or voltage, will generally be different for each path. This path dependence is a defining feature of non-conservative fields. The work done by the field and the corresponding potential difference varies with the route taken between 2 points. So, unlike conservative fields, where the voltage between 2 points is uniquely defined, regardless of how you move from one to the other, non-conservative fields can produce different voltage values depending on the path of integration. And this is one of the most important distinctions. In conservative fields, potential difference is a property of the endpoints, but in non-conservative fields, it's a property of the path. Unlike in a conservative field, if we move along a closed path within a non-conservative electric field, the total line integral is not equal to 0. As we traverse each infinitesimal segment along the loop, we can still evaluate the tangential component of the electric field. Building up a curve shows how this component varies around the path. But here's the key. The area under this curve, which represents the total work done by the field over the loop, is non-zero. This tells us that energy is either being added to or subtracted from the system, depending on the nature of the field. This behavior reflects a fundamental property of non-conservative fields. The circulation around the closed path is not zero. Now in a conservative electric field, the voltage difference between any 2 points depends only on their positions, not on the path you take to get from one to the other. No matter which route you follow from A to B, the work done and thus the potential difference is always the same. This path independence is a defining characteristic of conservative fields. But in a non-conservative electric field, that's no longer true. The voltage difference between the same 2 points does depend on the path. Taking different routes from A to B can result in different amount of work and therefore different potential differences. This path dependence is a hallmark of non-conservative fields, and it signals that the idea of a single well-defined electric potential simply does not apply in such cases. Kirchhoff's voltage law, or KVL, is only applicable in the context of conservative electric field, where the line integral of the electric field around any closed loop is guaranteed to be zero. In other words, the sum of the voltage drops and rises around the closed circuit loop must cancel out, and that's exactly what we'll talk about next. Let's take a step back into the 18th century. At that time, electrostatics had already been well established, thanks in large part to the work of Charles Augustin de Coulomb. His law described the force between stationary point charges, and from this it followed that the electric field E generated by static charges is conservative. In simple terms, this means that the work done by the electric field around any closed loop is zero, or equivalently, the line integral of the electric field around a closed loop is zero. This tells us something powerful. The electric field can be expressed as the negative gradient of a scalar potential, often called voltage. And this fundamental idea that the electric field in static conditions are conservative underpins much of early circuit theory. In fact, it's the foundation for one of the most widely used tools in electrical engineering, Kirchhoff's voltage law, or KVL. KVL states that the sum of the potential differences, or voltages, around any closed loop in a circuit is zero. This is really just a discrete circuit-level version of the continuous field idea that the closed-loop integral of E dot dl is 0 for a conservative electric field. As long as the electric field arises solely from static charge distributions with no time-varying magnetic fields involved, KVL holds true. Alongside KVL, we also have Kirchhoff's current law, or KCL, which says that the sum of currents entering a junction equals the sum leaving. This law is grounded in the conservation of electric charge, a principle that's fully consistent with Maxwell's equations. In steady-state conditions, like DC circuits or low-frequency AC systems, where charges don't significantly accumulate at a node, KCL is valid and forms a fundamental part of how we analyze electrical networks. But things changed dramatically with Faraday's discovery of electromagnetic induction. In the 1830s, Michael Faraday showed that a time-varying magnetic field can induce an electric field, even in the absence of any charge source. And this induced electric field is fundamentally non-conservative. Faraday's law, in its differential form, tells us the curl of the electric field is equal to the negative rate of change of the magnetic field. This result directly contradicts the core assumption behind Kirchhoff's voltage law. In systems with changing magnetic flux like transformers, generators, or any scenario with rapidly time-varying fields, the line integral of the electric field around the closed loop is not 0. So in these cases, KVL is no longer strictly valid. The sum of voltage drops around the loop doesn't equal 0. Instead, it equals the negative rate of change of magnetic flux through that loop. This marks a transition from electrostatics to electrodynamics. And while Kirchhoff's laws remain incredibly useful for most practical circuits, especially in DC and low-frequency AC systems, there are still approximations, valid only under certain assumptions. Negligible time-varying magnetic fields, negligible wave propagation effects, and lumped circuit elements. When those assumptions no longer hold, we must turn to the more fundamental and complete framework provided by Maxwell's equations. We'll dive into these assumptions in a moment to understand exactly when Kirchhoff's laws apply and what happens when the underlying conditions begin to break down. When a coil or electromagnet is connected to an alternating current AC generator, by closing the switch, it begins to produce a time-varying magnetic field. According to Faraday's law, this changing magnetic field induces an electric field, one that rotates in space, rather than pointing from one charge to another. Now, if you place a conducting ring around the coil and then close the switch, the sudden appearance of magnetic flux through the ring induces a rotating electric field. This electric field drives a current in the ring, and the direction of that current is such that it opposes the change in magnetic flux, as dictated by Lenz's law. Importantly, the induced current in the ring flows in the opposite direction to the current in the coil. And since opposing currents create magnetic fields that repel each other, a strong enough interaction can produce a repulsive force, powerful enough to launch the ring several feet into the air. The strength of this repulsive force depends on how much the current is induced, and that depends on the electrical conductivity of the ring. The more conductive the ring, the larger the current it can support, resulting in a stronger opposing magnetic field and a more dramatic jump. Now, if the conducting ring is instead held firmly in place, the rotating electric field from the coil continues to induce a circulating current through the ring. This current too depends on the ring's conductivity, and it continues to interact with the magnetic field from the coil. Here we have a set of rings, each made from a different material with a different level of electrical conductivity. In a ring with low conductivity, the changing magnetic field from the coil induces only a small circulating current. This induced current produces its own magnetic field, which partially opposes the coil's changing field. So instead of fully preserving the original magnetic field, a portion of it is cancelled out. This partial cancellation results in a weaker net magnetic field, which in turn leads to a weaker induced electric field. On the other hand, in a highly conductive ring, the induced current is much stronger. It produces a strong opposing magnetic field, which cancels out more of the coil's changing field. As a result, the net magnetic field becomes weaker, and the induced electric field becomes more perpendicular to the plane of the ring. As the conductivity increases, the ring can support more current in response to the changing flux. This greater current produces a stronger opposing magnetic field, which in turn weakens the net change, leading to a reduction in the rotating electric field. Now, in the ideal case, when the ring's conductivity approaches infinity, the induced current reaches its maximum possible value. And because the electric field is rotating, what really matters for driving current is its tangential component, the part that wraps around the ring. If the electric field is purely normal or perpendicular to the ring, there is no tangential component, and therefore no induced current. The induced electric field is strongest when it's entirely tangential to the ring. And here's the interesting part. The rotating electric field becomes effectively zero. Why? Because an ideal conductor doesn't require an electric field to sustain current flow. Even a negligibly small electric field is enough. You can think of it this way. The induced current needs an electromotive force, an electric field to support it. But as the conductivity increases, less and less field is required to maintain the same current. In the limit of a perfect conductivity, the required electric field approaches zero. In perfect conductors, the induced current is extremely large. So large that it generates an opposing magnetic field strong enough to completely cancel out the changing magnetic field coming from the coil. As a result, the net change of magnetic flux through the ring becomes zero. And according to Faraday's law, if the rate of change of the magnetic field is zero, then the resulting rotating electric field is also zero. So in a perfect conductor, the system responds in such a way that the changing magnetic field never reaches the interior of the conductor, and therefore no electric field needs to be induced to drive current. The current flows in response to the magnetic field trying to change, but never actually letting it change. Imagine a long wire carrying an alternating current, or AC. According to Ampere's law, this current produces a rotating magnetic field around the wire, circulating magnetic lines of force that encircle the current. Now suppose we introduce a small slot or gap in the wire. If the AC frequency is high enough, something interesting happens. The magnetic field around the slot remains nearly identical to that in the unbroken wire. So this raises a puzzling question. If no conduction current is flowing through the slot, what's producing the magnetic field in that region? To answer that, let's reimagine the slot as behaving like a capacitor. Two conductive plates separated by an insulator, which in this case is just air. As AC flows in a wire, charges build up in either side of the gap. Positive charges collect on one side, attracting negative charges to the other and repelling more positive charges away. This accumulation of opposite charges creates a time-varying electric field between the plates. And here's the key insight. A changing electric field gives rise to what James Clerk Maxwell called displacement current. Even though no actual charges cross the gap, the rate of change of electric flux in a region behaves as if a current were flowing. When you multiply this changing electric field, or more precisely, the changing electric flux, by the permittivity of the medium, you get something with the same units as current, amperes. This is exactly what was needed to maintain continuity in Ampere's law. Maxwell's addition of this displacement current term was revolutionary. It extended Ampere's law to include situations where no conduction current is present, showing that magnetic fields can be generated not only by moving charges, but also by time-varying electric fields. The AC current continues to flow through the wire even in the presence of the slot or the gap, because in one half cycle, the electric field pushes positive charges to one direction and pull it back in the other half cycle. Now let's take this one step further. Imagine the same slot in the wire, but instead of air between the ends, we insert a poorly conducting material, something like graphite. What happens? The magnetic field around the slot is still continuous and consistent with the field around the rest of the wire, but now the total current flowing through the system has two components: a conduction current flowing through the graphite and a displacement current arising from the time-varying electric field across the gap. And this is where the beauty of Ampere's law with Maxwell's correction truly shines. Magnetic fields can be generated by conduction current, displacement current, or both. As the conduction current increases through the poorly conducting material, the accumulation of charge at the terminals decreases. This reduction in the accumulated charge leads to a decrease in the electric field and, consequently, displacement current. As more conduction current flows, a portion of the previously accumulated charges begins to move through the material in the form of current. If the material between the wire ends is highly conductive, the conduction current dominates. If it's a poor conductor, displacement current dominates. This idea is key to understanding how capacitors conduct AC current, even though their plates are separated by an insulator. It's not that charges leap across the gap, rather the changing electric field between the plates does the work, sustaining the magnetic field and maintaining the continuity in the system. Even though displacement current isn't a real current in the sense of moving charges, it plays a very real role in generating magnetic fields. In fact, it's one of the cornerstones of how electromagnetic waves propagate through into space. Now let's take things a step further. Suppose you bend the wire into a loop, still carrying an AC current. What happens to the magnetic field? The same principles apply. On the left side of the loop, the current creates a magnetic field into the plane. On the right side, the current also creates a magnetic field into the plane. These contributions reinforce one another inside the loop, producing a strong, consistent magnetic field at the center. But remember, the current is alternating, changing direction every half cycle. So the magnetic field also alternates, pointing upward in one half cycle and downward in the next. If you look at the loop from the side, something fascinating emerges. A current loop behaves like a magnetic dipole. It has a north pole and a south pole, just like a bar magnet. So as soon as you form a loop of current, you've created a magnetic dipole. Now revisit the idea of a slot in the wire. Even with a gap in the loop, the magnetic field remains continuous. Why? Because the gap is filled not by conduction current, but by displacement current, driven by the changing electric field across that region. So you have conduction current flowing inside the wire, and displacement current crossing the gap. Both contribute to the same magnetic field, bridging the loop without breaking the field lines. Now imagine replacing the air gap with graphite. Here's what happens. Part of the current flows as conduction current through the graphite. The rest exists as displacement current from the time-varying electric field. Together, these two components form a total current that behaves seamlessly, producing a continuous magnetic field, just as if the wire had never been broken. Now let's consider the opposite scenario. This time, imagine we don't have any current flowing in a wire loop initially. Instead, we introduce an oscillating magnetic field through the center of the loop. According to Faraday's law of induction, a changing magnetic field induces an electric field, which in turn drives an electric current around the loop. So everything still works the same way, but now the mechanism is reversed. Instead of current creating magnetic field, a magnetic field is generating current. If the loop is continuous, the induced electric field produces a circulating conduction current in the wire. But if there's a slot or gap in the loop, something interesting happens. To maintain a continuous magnetic field across the loop, nature fills in the gap, not with conduction current, but with displacement current, just as before. Even though no actual charge crosses the gap, the changing electric field in that region acts like a current, ensuring that the magnetic field remains unbroken and behaves exactly as it would in a continuous loop. Now, if we place a poorly conducting material like graphite in a gap, the total induced current divides into two components. One part becomes conduction current through the weakly conductive material. The other remains a displacement current due to the time-varying electric field across the gap. This shows that Maxwell's displacement current isn't just a mathematical fix for Ampere's law. It's a fundamental physical concept that explains how electric and magnetic fields interact in both directions. A changing electric field generates a magnetic field. A changing magnetic field induces an electric field. In both cases, whether the system is driven by a current or by a field, the presence of displacement current ensures that the electromagnetic behavior remains continuous and consistent, even when the geometry involves gaps, insulators, or poor conductors. Now let's explore a more detailed and realistic setup. Imagine a copper loop that contains two resistors, one in each side. The left resistor has a resistance of 100 ohms, while the right resistor is significantly larger at 900 ohms. Inside this loop, we place a solenoid, a coil of wire connected to a sinusoidal voltage source through a switch. When the switch is closed, the solenoid generates a time-varying magnetic field, specifically one that oscillates sinusoidally. According to Faraday's law, this changing magnetic field induces a current around the loop. Initially, this induced current is a conduction current, flowing freely through the copper wire. But when it reaches the right-hand resistor, the current is split into two parts. One part continues as conduction current, flowing through the resistor. The other part takes the form of a displacement current arising from the changing of electric field across the resistor. But why displacement current in a resistor? Even though a resistor is a conductor, it also exhibits capacitive effects, especially at higher frequencies. Due to the accumulation of charge we talked about previously, you can think of it like this. The copper wires in either side of the resistor act like conductive plates, and the resistor material in between behaves like a poor dielectric. In this analogy, an ideal dielectric, like air or vacuum, would block conduction entirely and allow only displacement current. A poor dielectric, like the resistor, allows some conduction but also supports a small displacement current due to the changing electric field. So, in a 900 ohm resistor, the conduction current is relatively low because the resistance is high. A displacement current arises as well, but it's less dominant as the resistor is a poor dielectric. At the end of the resistor, these two components, conduction and displacement currents, recombine in a copper wire and continue forward as a single conduction current. When this current reaches the left resistor, the 100 ohms, the same process occurs, but now under different conditions. The resistance is lower, so the conduction current is higher, and the displacement current is smaller. The resistance is lower, so the conduction current is higher, and the displacement current is lower. Once again, at the end of the resistor, the two current components merge into a conduction current completing the loop. You can represent this entire system with an equivalent AC circuit model. The changing magnetic field from the solenoid acts like a current source as it drives the loop current through electromagnetic induction. On the right side, we model the 900 ohm resistor as a resistor in parallel with two small capacitors, which represent the displacement currents inside and outside the loop. The electric field in both sides of the resistor. On the left side, the 100 ohm resistor is also in parallel with two small capacitors, again modeling the inner and outer displacement paths. It's important to highlight that displacement current is frequency dependent. At low frequencies, the capacitance reactance is high, meaning the capacitors resist current flow. In this case, most of the current flows through the resistor as conduction current, and displacement current is minimal. At high frequencies, the capacitance reactance drops, allowing more displacement current to flow. This is just like in real capacitors, where at high frequencies, capacitors allow more AC current to pass through. Also remember one key property of capacitors. Current leads voltage by 90 degrees. That means the displacement current leads the conduction current, which is typically in phase with voltage by a quarter cycle. So as you can see, literally through the animation, we're observing a complete dynamic electromagnetic system where magnetic fields induce electric currents, those currents interact with resistive and capacitive elements, and the overall current flow is a mix of conduction and displacement currents, shifting and adjusting with frequency. As you can see, there's no displacement current in most parts of the circuit, and therefore no electric field around the loop, except in the regions of the left and the right resistors. In the right resistor, the displacement current is greater than in the left one. This means the time-varying electric field across the large resistor is also stronger than that across the smaller resistor. As we've discussed before, voltage is defined as the line integral of the electric field along a path. So a strong electric field across the right resistor leads to a higher voltage drop across it compared to the left resistor. Now let's consider the copper wires. Since copper is a good conductor, there's essentially no electric field across these sections, meaning the voltage drop along the copper is zero. If we now sum the voltage drops around the entire loop, we find that they don't add up to zero. This tells us that Kirchhoff's voltage law, or KVL, does not hold in this scenario. To understand why, let's analyze the voltage between 2 points in the circuit, point A and point B, taking two different paths. Right path, you go through a copper wire, 0 voltage drop, then through the large resistor, positive voltage drop, then again through copper, 0 drop. Left path, you again pass through copper, 0 drop, then through the small resistor, But here the electric field is in the opposite direction of the path, so you get a negative voltage drop and then through copper again. Surprisingly, you get two different values for the voltage between points A and B depending on which path you take. This is unexpected from the traditional viewpoint of conservative electric fields. The reason lies in the nature of the electric field in this setup. The field is not conservative because the curl of the electric field is not zero, meaning the field is rotating. Even though the electric field in the copper is extremely small, it's not exactly zero. This tiny field contributes to a non-zero closed-loop integral, meaning the electric field cannot be written as the gradient of a scalar voltage function. As a result, voltage is not well defined in this case, and the foundational theory of gradients does not apply. Therefore, voltage becomes path-dependent and KVL fails. This experiment is the same as the one demonstrated by Dr. Walter Lewin in lecture 16 of his Electricity and Magnetism course. He illustrated a situation where Kirchhoff's voltage law appears to break down, highlighting that it's not universally applicable. Instead, Faraday's law provides a more general and fundamentally accurate description of the behavior of electric field in such scenarios. He used this demonstration to show that KVL is a special case of Faraday's law, valid only when electric field is conservative, that is, when there is no time-varying magnetic field present.
And here is A, and you go this way, you find 0.9 volts plus. If you go this way, you find minus 0.1 volts. Faraday has no problems with that. Kirchhoff has a problem with that. But who cares about Kirchhoff? Faraday is the law that matters, because Faraday's law always holds. Because if the phi dt is zero, then you get Kirchhoff's. Kirchhoff's rule is simply a special case of Faraday's law, and Faraday's law always holds. So Kirchhoff is for the birds, and Faraday is not.
Previously, we observed that due to charge accumulation, a displacement current arises across resistors. As a result, the conduction current before the resistor is not equal to the current flowing through the resistor itself. This implies that if we consider only conduction current, Kirchhoff's current law doesn't hold, since the current entering the node just before the resistor doesn't equal the current leaving it. A similar situation occurs at the node after the resistor. The conduction current inside the resistor is less than the conduction current flowing out. Thus, once again, if only conduction current is considered, KCL appears to be violated. That's why we introduced capacitors in the model, in parallel with the resistors to account for the displacement current. These capacitors model the effect of charge accumulation and allow us to represent the total current, conduction plus displacement, correctly. With this modeling approach, the total current entering the node before the resistor equals the sum of the conduction current through the resistor and the displacement current through the capacitor. Similarly, the current flowing out after the resistor equals the sum of the conduction current and the displacement current. So KCL can be made to hold in this setup by accounting for the displacement current, which was introduced approximately 20 years after KCL. Without including the displacement current, KCL would not be valid in this context. Now let's return to the equivalent circuit model. We'll test this model using a SPICE simulator to verify whether it accurately represents the loop in our experiment. Recall that an ideal current source delivers a specified amount of current regardless of the voltage across its terminals. It adjusts the voltage as necessary to maintain the required current to flow. The current source in the circuit represents the current flowing through the copper sections of the loop. Since there is no significant voltage drop across the ideal copper conductors, let's assume that the voltage across the current source is zero. The circuit consists of three key nodes, A, B, and C, where nodes A and B are located across the current source, and node C is at the bottom of the loop. Given our assumption that the voltage across the current source is zero, the potential difference between nodes A and B is also zero. Now suppose the current source delivers a step current that rises from 0 to 1 mA within 1 nanosecond. If we measure the voltage between nodes A and C and between B and C, which correspond to the voltages across the 100 and the 900 ohms resistors respectively, we observe the following. The voltage across the 900 ohm resistor between A and C will be 0.9 volts, and the voltage across the 100 ohm resistor between B and C will be minus 0.1 volts. This implies that if we assume the current source has zero voltage across it, we end up with two different voltage values between the same 2 points in the loop. As a result, KVL no longer holds under this assumption. However, this situation cannot occur in the SPICE simulations because SPICE uses the lumped element model and relies on classical circuit theory like Ohm's law and Kirchhoff's laws to analyze circuits. To maintain consistency with Kirchhoff's voltage law, the current source in SPICE will adjust the voltage across its terminals as needed to ensure the specified current continues to flow. In this case, for KVL to hold, the voltage across the current source must be 1 volt, which is the sum of the voltage drops across the 100 and the 900 ohm resistors. This 1 volt corresponds to the change of the magnetic field in the physical experiment. One might ask, why not simply replace the current source with a voltage source whose value equals the rate of change of the magnetic field in the experiment? Doing so would ensure that the voltage between points A and B is the same regardless of the path taken, and KVL would hold throughout the circuit. However, this approach fails to accurately represent the physical behavior of the loop in the experiment. In the actual experiment, the induced electric field is rotational. It forms closed loops due to the time-varying magnetic field. This means the electric field has a non-zero curl and is therefore non-conservative. The current in the loop is also rotational, circulating as a result of this induced field. In contrast, introducing a voltage source into the model enforces a different kind of electric field behavior. Outside the voltage source, the electric field points from the positive terminal to the negative terminal. Inside the source, the electric field goes in the reverse direction, from positive to negative. This creates two opposing electric fields within the loop. When integrating around the entire closed path, these fields cancel each other out, resulting in zero net circulation. In other words, the electric field in this model does not form a continuous loop. It does not rotate as it does in the physical system. As a result, the electric field in this model is conservative, and the system adheres to KVL and traditional circuit theory. But because it lacks the rotational field characteristics of the experimental setup, it doesn't accurately represent the underlying physics of the real loop. In a rotational, non-conservative electric field, such as the one induced by a time-varying magnetic field, the current circulates in a closed loop, effectively rotating back to itself. This means that the voltage between 2 points, such as points A and B, depends on the path taken. For example, to sustain a clockwise circulating current, the voltage between A and B in the right branch must be positive, while in the left branch it must be negative. This voltage difference across paths is essential to support the loop current flow. If, instead, the voltage between A and B is well-defined and path-independent, then the current in both branches would flow from A to B in the same direction. In such a case, there would be no rotating current, just a unidirectional flow guided by the imposed voltage. While it's true that the time-varying magnetic fields induce rotating currents as established by Faraday's law, for such currents to exist, the voltage between points A and B must vary depending on the path, which is a direct consequence of the non-conservative nature of the induced electric field. The curl of E is non-zero. In contrast, in a lumped element circuit model, we are enforcing a conservative electric field. Here the electric field points from the positive to the negative terminal of the source, both outside and inside the source. These fields oppose each other, effectively cancelling out in a closed-loop integration. Neither the electric field nor the current is rotating. As a result, the voltage between any 2 points in the circuit is uniquely defined and independent of the path taken. For instance, in such a model, the voltage between points A and B across the voltage source is the same whether measured through the right or the left branch. If point B is slightly shifted downward, the voltage along the right path decreases due to a reduction in the electric field length, but the voltage along the left path decreases by the same amount. This happens because the electric field from point B to C opposes the internal electric field from the voltage source, reducing its contribution equally in both paths. Therefore, in a lumped element circuit with a conservative electric field, the voltage is well defined and path independent. This stands in contrast to Dr. Walter's experiment, where the electric field is non-conservative due to the time-varying magnetic field, making the voltage between 2 points path-dependent and enabling the formation of rotating currents. The experimental setup involves a non-conservative electric field and a rotating current, effects that a lumped element model cannot accurately capture. This behavior lies beyond the scope of traditional circuit theory, which rests on the assumption of conservative fields and path-independent voltages. We'll examine these limitations in greater depth in Part 2, where we'll unpack exactly why lumped element modeling breaks down in this scenario. So to wrap things up, when the loop encloses a time-varying magnetic field, the induced electric field is non-conservative. It cannot be expressed as the gradient of a scalar potential, which makes the potential difference between 2 points path-dependent. As a result, the voltage between those points can take infinitely many possible values, each determined by the path chosen for integration. In circuits containing resistors exposed to time-varying magnetic fields, charge may accumulate across the terminals, giving rise to a displacement current. This displacement current subtracts from the conduction current, meaning the total current at a node is no longer purely due to moving charges in conductors. Under these conditions, Kirchhoff's current law, or KCL, which assumes that the conduction current is conserved at a node, breaks down and no longer valid. This assumption fails when displacement current becomes significant due to the presence of time-varying electric fields. Similarly, because the induced electric field is non-conservative, voltage is no longer well-defined as scalar quantity, and Kirchhoff's voltage law, or KVL, which relies on no circulation of conservative electric fields around closed loops, also fails to hold. Kirchhoff's voltage law, or KVL, is actually a special case of Faraday's law of electromagnetic induction. When there is no magnetic field passing through the loop, or when the frequency is very low, the rate of change of the magnetic flux becomes negligible. That means the right-hand side of Faraday's law drops to zero. Same thing happens if the permeability is zero. When the permeability of a material approaches zero, the speed of wave propagation becomes extremely large. This is because the speed of an electromagnetic wave is given by 1 over the square root of mu epsilon, where mu is the permeability and epsilon is the permittivity of the medium. If either mu or epsilon approaches zero, the wave speed tends toward infinity. An infinite wave speed implies that, for a given finite frequency, the wavelength becomes extremely large. In practical terms, this means the wavelength is much larger than the dimension of typical circuit elements. So when the wavelength is much larger than the circuit element dimensions, right-hand side of Faraday's law becomes zero. Either one of these cases leads to a great simplification to Faraday's law, making the curl of electric field equal to zero. Therefore, if we have a circuit like this, the line integral of E around any closed curve which does not pass through any of the elements is zero. The line integral of the electric field E around the closed curve can be broken down into several segments. Each segment corresponds to the line integral taken across a specific circuit element from one terminal to the other. This segment of the line integral is what we refer to as the voltage drop across the circuit element. Since the line integral of the electric field around a closed loop is zero, the sum of the potential differences or voltage drops across all elements in the loop must also be zero. In other words, the total line integral is simply the sum of the voltage drops across each circuit element, and this sum equals zero. Notice that zero curl means that the electric field is the gradient of potential function, meaning the potential of the two terminals of any component is defined. The difference of these two potentials is what we call the voltage difference, or simply the voltage. This result is valid only under certain conditions, specifically at low frequencies, where the wavelength is much larger than the dimensions of the circuit, or in regions where magnetic fields are absent. Under these conditions, the line integral of the electric field around any closed loop is equal to zero. Kirchhoff's current law can be derived as a special case of the generalized Ampere's law, which includes Maxwell's correction for displacement current. The generalized Ampere's law is given by this equation. Here J is the conduction current density, and epsilon naught times the partial derivative of E with respect to T is the displacement current density introduced by Maxwell. In the case of a stationary or low-frequency system, where the electric field does not change significantly with time, the displacement current term becomes negligible. Partial derivative of E is zero. If the permittivity is negligible, the wave speed becomes very large, implying effectively instantaneous electromagnetic propagation. Equivalently, this corresponds to the quasi-static limit where the wavelength is much larger than the circuit dimensions. In this case, the displacement current term again becomes negligible. Under these conditions, Ampere's law simplifies to its original form. Taking the divergence of both sides, but the divergence of a curl is always zero. This leads to the continuity equation, which states that the net current flowing into any point in the circuit is zero. A direct expression of Kirchhoff's current law. This means that at any junction in an electrical circuit, the total current entering the junction equals the total current leaving it. Thus, KCL is not just an empirical rule. It arises naturally from Maxwell's equations under the appropriate physical assumptions. Now suppose we have a circuit like this. One of the common idealizations in circuit theory is that negligible electrical charge accumulates at the terminals of the circuit elements. We further assume that any charge accumulation on the connecting wires between these elements is also negligible. Under these assumptions, the principle of charge conservation implies that any charge leaving one circuit element must immediately enter another. In other words, the total charge within the circuit remains constant at all times. This leads directly to the requirement that the algebraic sum of the currents entering any junction in a circuit must be zero. This is the essence of Kirchhoff's current law, which states that the net current flowing into a node is equal to the net current flowing out. Now let's take a step back and examine this setup from a new angle. At time t equals 0, the magnetic field begins to increase. This changing magnetic field induces a uniform rotating electric field. That rotating electric field, in turn, gives rise to conduction currents. Currents that vary depending on the electrical conductivity of the material. Currents that vary depending on the electrical conductivity of the material. Among the segments in our system, the right segment has the lowest conductivity, so it carries the smallest conduction current. The left segment has a higher conductivity and carries a larger current. Finally, the copper segments with the highest conductivity carry the largest conduction currents. Now, here's where it gets interesting. Conduction current is essentially the rate at which electric charge moves. So when charge enters the right segment at a higher rate than it can travel through it, charge begins to accumulate at the junctions. Specifically, at the boundaries between materials of different conductivities. If charge enters a region faster than it exits, positive charge accumulates. Conversely, if it exits faster than it enters, negative charge builds up. These accumulated charges generate an electric field, pointing from the region of positive charge to the region of negative charge, since the magnetic field is sinusoidally changing. The induced electric field and the conduction currents are also sinusoidal. As a result, the accumulated charge and its corresponding electric field also vary sinusoidally over time. This means the polarity of accumulated charge reverses once every cycle, and so does the direction of electric field. Now, here's the key insight. The rate of change of this time-varying electric field is what we call the displacement current. So inside the resistive segment, we have a conduction current due to the movement of real charges, and the displacement current due to the time-varying electric field created by charge accumulation. The sum of these two currents equals the total current in each copper segment. In other words, the system behaves as if there is a capacitor in parallel with a resistor. Some of the current entering the junction flows through the resistor as conduction current, while the rest flows through this parasitic capacitor as displacement current. Now let's talk about voltage. The electric field resulting from charge accumulation indicates the local voltage. In fact, voltage is defined as the line integral of the electric field from one point to another. So the stronger the electric field, the higher the voltage across that segment. A higher resistance restricts current flow, causing more charge to accumulate at the junctions. This leads to a stronger electric field, and therefore a higher voltage across that segment. You may ask, why use a sinusoidal excitation when Dr. Lewin's experiment was based on a step response? Well, the reason is both practical and fundamental. A sinusoid is the most basic and pure form of a signal. It's smooth, continuous, and extremely well behaved in both time and frequency domains. More importantly, it serves as the building block of all signals. Thanks to the Fourier series and Fourier transform, we can represent any signal, including a step function, as a combination of many sinusoids, each with its own amplitude, frequency, and phase. So when we analyze a system's response to a sinusoid, we're not simplifying or deviating from reality. We're uncovering how the system responds to each frequency component individually. And once we know that, we can reconstruct the system response to any signal, even a sudden step. Think of it this way. A step function is just a bunch of sinusoids layered together. By studying how the system reacts to each layer, we gain full insight into its behavior under the step. If you'd like to explore this concept further, I've created a dedicated playlist on Fourier series and Fourier transform where I explain how complex signals are broken down and rebuilt from sinusoids. So even though we're using a sinusoidal input here, we're still capturing the essence of how the system behaves under any form of excitation, step response included. Now in Dr. Lewin's experiment, the setup remained the same, except that the solenoid was excited using a step function instead of a sinusoidal input. The step function transitioned from 0 to its maximum value in approximately 10 milliseconds.
The magnetic field, as a function of time, will come up like this and will then reach a maximum. So the change of the magnetic field, dB dt, is going to be something like this. So it's the derivative of this curve. And that is proportional with the induced EMF, and that's proportional with the current, to Ohm's law. From here to here is about 10 milliseconds.
A voltmeter was connected to measure the voltage between points A and B. Initially, the voltmeter was placed on the right side, across the 900 ohm resistor, measuring the voltage drop across it. Then, the voltmeter configuration were flipped, so that the voltmeter now measured the voltage across the 100 ohm resistor in the left, still between the same points A and B. Despite measuring the voltage between the same 2 points in both configurations, the voltmeter displayed different voltage readings. This surprising result highlighted an apparent discrepancy. Different voltage measurements across the same 2 points, depending on the placement of the voltmeter.
I attach a voltmeter here. That voltmeter will show me plus 0.9 volts. Now I attach a voltmeter here. The same one. I flip it over. It's connected between point D and point A. It will read minus 0.1 volt. This voltmeter, which is connected between D and A, reads plus 0.9. This voltmeter, which is connected to D and A, reads minus 0.1.
But what exactly is a voltmeter, and what does it measure? In its simplest form, a voltmeter is a device with a high internal resistance designed to measure the voltage across 2 points in the circuit. It operates by allowing a small current to flow through its internal resistance, which causes a deflection in a needle proportional to that current. The scale of the voltmeter is calibrated to display the voltage according to Ohm's law. V equals IR, where R is the internal resistance of the voltmeter. When current flows from the positive terminal to the negative terminal of the voltmeter, the needle deflects clockwise, indicating a positive voltage. Typically, the internal resistance of a voltmeter is made much higher than the resistance of other components in the circuit, and that to minimize the effect of the voltmeter in the circuit. Voltmeters are always connected in parallel with the component across which the voltage is to be measured. What the voltmeter actually measures is the voltage drop across its own internal resistance, again using Ohm's law. You can think of the voltmeter reading as the line integral of the electric field, where the path of integration passes through the meter, beginning at the red lead and ending at the black one. For instance, in this circuit, the voltmeter reads the line integral of the electric field through the meter. Since there is no magnetic flux, then the curl of E is equal to 0 and the electric field is conservative. So the line integral of E is independent of the path, and the potential is defined at point A and B, and the voltage is the difference between VA and VB. The closed-loop line integral of the electric field is equal to the negative rate of change of the magnetic flux through the loop. And so, the sum of the line integrals along the path from point A to point B through the right segment and from point B back to point A through the left segment is equal to the negative time derivative of the magnetic flux enclosed by the loop. This is a direct application of Faraday's law. If we add a voltmeter to the left, the voltmeter with the right segment will form a closed loop. The sum of the line integrals along the path from point A to point B through the right segment and from point B back to point A through the voltmeter is equal to the negative time derivative of the magnetic flux enclosed by the loop. From these two equations, we notice that the line integral of the electric field through the meter is equal to the line integral from A to B through the left resistance. So the meter in this configuration measured the potential difference from A to B through the left resistor, the left path. Similarly, we can conclude that if move the voltmeter to the right, it will measure the potential difference between point A and B through the right resistance, or the right path.
3, 2, 1, 0. Look on the left, there's V1. Notice, it's negative. Look on the right, there's V2. It's about 9 times larger than V1. The moment that the magnetic field reaches a maximum and remains constant, there is no longer any induced current.
I support Dr. Walter's findings and conclusions, and appreciate the clarity of his analysis. However, I respectfully interpret certain parts of the explanation differently based on my understanding. Dr. Walter assumes that the current flowing through the resistors is equal and identical to the current flowing through the connecting copper wires.
So now I ask you, what is the current? Ohm's law holds. The induced EMF is 1 volt, and R1 plus R2 is still 1000 ohms, so 10 to the minus 3 amperes. I really make a nuisance of myself and I say, what is VD minus VA? And you get annoyed at me and you say, look, the current I through R2, Ohm's law, V equals IR, plus 0.9 volts.
I disagree with this assumption. Once the current reaches the 900 ohm resistor on the right, it should, in my view, divide into two components. One component is the conduction current that flows through the resistor, and the other is the displacement current, which arises from the time-varying electric field due to charge accumulation at the ends of the resistor, as previously discussed. A similar division occurs at the left resistor. However, since the left resistor has a lower resistance, 100 ohm compared to the 900 ohms, the conduction current through the left resistor will be greater than that through the right resistor. It's important to note that displacement current depends on the frequency of the applied signal. In Dr. Walter's experiment, the step input voltage reaches its maximum in about 10 milliseconds. This corresponds to a highest frequency component of roughly 35 Hz, which is relatively low. Therefore, in this case, the displacement current is negligible for practical purposes. However, it does exist and should be considered if more precise analysis is desired. Furthermore, the magnitude of the displacement current becomes more significant with faster rise times in the step input. That is, if the switch is activated more rapidly, the higher frequency components increase, and so does the displacement current. Kirchhoff's current law assumes the conservation of charge and that there is no charge accumulation at any node. However, at high frequencies, this assumption breaks down due to parasitic effects such as charge accumulation at the boundaries of components like resistors. As a result, KCL may no longer be strictly applicable in high-frequency circuits. That being said, at high frequencies, not only does Kirchhoff's voltage law becomes unreliable, but Kirchhoff's current law also breaks down. In my opinion, any analysis aiming to demonstrate the limitations of KVL at high frequencies should avoid relying on KCL, as both laws are approximations derived from Maxwell's equations and are not strictly valid under high-frequency conditions. In a lumped element model of circuit analysis, we make several idealizations to simplify how inductors behave. 1. Magnetic field containment. We assume that all magnetic fields generated by the inductor are completely confined within the coil itself. That is, the magnetic field in a region outside the coil, especially near the terminals A and B, is negligible. 2. Negligible resistance. The wire used in the inductor is considered to have no electrical resistance. 3. Negligible surface charge effects. Any surface charge that accumulates on a wire, which could contribute to the buildup of electric fields, is assumed to be negligible. But why is V equals L di dt? When a current flows through an inductor, it generates a magnetic field that is proportional to the current. If the current changes over time, so does the magnetic field. According to Faraday's law of induction, a changing magnetic field induces an electric field. This means the line integral of the electric field E around the closed loop is equal to the negative rate of change of the magnetic flux through that loop. Now consider a specific path for this line integral. Start at terminal A, move through the coil to terminal B, always staying inside the conductor. Return from B to A through the space outside the inductor. Since the coil is made of a perfect conductor, there can be no electric field inside it. Any electric field would produce infinite current. So the integral of the electric field along the path through the coil from A to B is 0. Thus, the entire contribution to the line integral comes from the path outside the coil, from B to A through the air. But we've assumed that the magnetic field outside the coil is negligible, so the value of this integral is independent of the exact path taken. This allows us to define the voltage difference between terminals A and B. This voltage difference is what we refer to as the electromotive force, or EMF. Since the magnetic flux is proportional to the current through the inductor, we have this equation. Taking the sign convention into account for passive elements, we write the voltage across the inductor as V equals L di dt. This explanation of the ideal inductor exemplifies the lumped element approach in circuit theory. In this framework, each component, resistor, capacitor, or inductor, is described solely in terms of voltages and currents at its terminals, abstracting away the complex electromagnetic interactions inside and around the element. In this circuit, as long as there is no magnetic field present in the region outside the individual circuit elements, the line integral of the electric field E around any closed path that does not pass through any of the elements is 0. This closed line integral can be broken down into segments, each corresponding to the path between the terminals of a circuit element. Each of these segments represents the line integral of E across the element, which we refer to as the voltage drop across the element. Therefore, the total line integral around the entire loop is simply the sum of the voltage drops across all the elements in the circuit. All the textbooks Dr. Walter referred to, contrary to how he explained it, seem to be correct in their approach. The closed loop used for taking the line integral of the electric field is a path that does not pass through any of the circuit elements. In doing so, they treat components like inductors as lumped elements, meaning the behavior of the inductor is fully described in terms of the currents and voltages at its terminal, without accounting for the complex electromagnetic fields that exist inside it. This simplifies analysis, avoiding the path through the inductor, through which the line integral is 0. ElectroBOOM repeated the same experiment and obtained the same results, but he arrived at a different interpretation.
Now the sense wires are on the 10 kilo ohm side. Click. See, I have a voltage pulse with a peak of around 25 millivolts. Now all I do is I flip the sense wires to the 1 kilo ohm side of the loop. Click. We have a negative pulse around 1/10 of the first pulse.
Like Dr. Walter, he did not mention the displacement current.
Because although the current in the loop is the same, the resistance is 1/10.
Displacement current is negligible in his low-frequency experiment. However, at higher frequencies, the displacement current becomes significant and should be considered. To further investigate, he measured the voltage drop across the wire connecting the loop to check for any induced voltage.
I move the sense wires across the loop wire. Click. The scope just triggers a noise. There is no voltage across the wires.
He then repositioned the resistors, placing them close together, and repeated the measurements. When he measured the voltage drop across each resistor individually, by placing the probes directly at the boundaries of the resistors, thus excluding the loop wire, he observed the same results as before. Measuring across both resistors together, he obtained the sum of the voltage drops across R1 and R2.
See, it's actually higher than 25 millivolts. Pretty close to 27.5.
Despite having measured the zero voltage across the loop wire, he concluded that the voltage across the loop wire is equal to the sum of the voltage drops across R1 and R2.
This shows that the voltage across the loop is not zero, unlike what we thought, but is equal to VR1 plus VR2. The loop is the secondary of a transformer, with the primary being my coil. Dr. Levin's model misses a transformer in the loop, with the voltage across the winding equal to VR1 plus VR2. KVL holds.
This conclusion contradicts his own measurement after repositioning the resistors, where he again confirmed that the voltage across the connecting loop wire was 0.
If instead of measuring locally like this, we measure across the loop on the other side, we would read 0 volt across the loop.
According to ElectroBOOM's experiment, an intriguing observation arises when measuring the voltage across 2 points in the loop. The result depends on where the measuring leads are connected. When the measurement is taken from the side of the resistors, a voltage of 27.5 millivolts is observed. However, when the measurement is taken from the side of the loop wire, the voltage reads 0.
If instead of measuring locally like this, we measure across the loop on the other side, we would read 0 volt across the loop, which is correct. So which one is right?
This discrepancy is significant and leads to an important conclusion. The voltage between these 2 points is path-dependent, indicating that the electric field in this region is non-conservative. This occurs because the loop encloses a time-varying magnetic field. As discussed earlier, a changing magnetic field induces a circulating non-conservative electric field, which cannot be described as the gradient of a scalar potential function. Therefore, I disagree with the assertion that KVL holds in this configuration. In the presence of a time-varying magnetic field enclosed by the loop, KVL does not hold in its traditional form. So which one is right?
If instead of measuring locally like this, we measure across the loop on the other side, we would read 0 volt across the loop, which is correct. So which one is right?
Both are right. In fact, this is exactly what Walter Lewin concluded. What you're measuring is 2 different voltage values between the same 2 points, because the measurement follows 2 different paths. I know I've repeated this several times, but it's important, so let me state it once more. In this experiment, the electric field is non-conservative. As a result, the line integral of E to dl depends on the path taken. If you measure the voltage along one path, you obtain a certain voltage. If you measure it along a different path, connecting the same 2 points, you obtain a different voltage. This is not a contradiction. It's precisely the behavior expected from a non-conservative electric field. The measured potential difference is path-dependent, so different measurement paths can legitimately produce different voltage readings, even though the endpoints are the same. Let me illustrate this visually. According to Faraday's law, a time-varying magnetic field generates a circulating electric field. If a closed loop made of a perfect conductor is placed in this field, the induced electric field drives a current around the loop. This induced current produces its own magnetic field, which, according to Lenz's law, opposes the change in magnetic flux that generated it. As a result, the induced magnetic field reduces the net variation of the magnetic flux through the loop. In the ideal case of a perfect conductor, the current adjusts itself so that the magnetic flux through the loop remains constant in time, causing the net electromotive force around the loop to vanish. Consequently, the circulating electric field is cancelled within the conductor by the fields produced by the induced charges and currents, resulting in 0 tangential electric field inside the conductor. Therefore, the electric field at the conductor surface is effectively perpendicular to the wire, with no component along the direction of the conductor. Since the voltage around the closed path is given by the line integral of the electric field along that path, the absence of any tangential electric field along the ring implies that this integral is 0, and hence the net voltage around the ring vanishes. So if you connect a voltmeter across any 2 points in this loop, it will read 0 volts. Now let's look at the setup after the resistor is repositioned. We have the loop wire, a 900 ohm resistor, and a 100 ohm resistor. Along the loop wire, the induced electric field is perpendicular to the wire, so there is no tangential component along the loop itself. As a result, the line integral of the electric field around that path is 0, meaning the voltage between points A and B measured on the loop side is 0. On the resistor side, however, There is a tangential electric field along the path from A to B. Therefore, the line integral of the electric field is non-zero, and the voltage exists between A and B. Moreover, different paths from A to B on the resistor side encounter different electric field distributions, so the line integral, and therefore the measured voltage, depends on the chosen path. In other words, different paths can yield different voltage readings. This again confirms Dr. Lewin's conclusion. In the presence of a non-conservative electric field, voltage is path-dependent and cannot be uniquely defined between 2 points without specifying the path. That being said, it is possible to approximate conditions under which KVL becomes valid. Again, consider a scenario where the two resistors are placed in a close proximity to each other, and effectively outside the region of the changing magnetic field. In this case, the loop can be modeled as a single-turn inductor, akin to the secondary winding of a transformer, while the solenoid acts as the primary. By ensuring that the magnetic field is confined only within the inductor or the loop wire and negligible elsewhere, particularly around the resistors, we can assume that the electric field outside the inductor is conservative. This approximation allows us to define voltage differences across components, and under these conditions, KVL holds again. To conceptualize this, consider that a time-varying magnetic field generates a circulating electric field, described by Faraday's law. In a perfect conductor like a loop wire, any internal electric field would induce infinite current, which is non-physical. Thus, the line integral of the electric field inside the conductor is zero. The entire contribution to the induced voltage arises from the external path through the air. But if we assume that the external magnetic field is negligible, this integral becomes independent of the exact path, making it possible to define a voltage difference between the terminals of the inductor. So, KVL can be applied, but only under these approximations. If we don't carefully arrange the circuit to isolate the changing magnetic field within the loop, then these assumptions break down. In such cases, where a time-varying magnetic field is enclosed by the loop, circuit theory becomes invalid. Traditional circuit analysis assumes no time-varying magnetic fields outside components, no net charge accumulation inside components. Component dimensions are much smaller than the wavelength of the signals involved. These assumptions are often necessary for engineers to design practical circuits without resorting to the full complexity of Maxwell's equations. While those equations offer the most accurate model, they are often cumbersome for everyday circuit design. In conclusion, I believe the main point of the experiment is to demonstrate that KVL fails in the presence of non-conservative electric fields, and I completely agree with that takeaway. Without rearranging the resistors to exclude them from the influence of the time-varying magnetic field, it is not possible to make the necessary approximations for KVL to hold.
Dr. Lewin's theory is not dependent on the location of the resistors, so let's rearrange them. Here I move the resistors side by side and very close.
Remember that this is only an approximation. We assume the magnetic field is strictly confined within the loop, which allows us to treat the external electric field as conservative and apply standard circuit theory. In reality, this is an oversimplification. To make circuit design practical, engineers frequently rely on such assumptions to gain intuition and bypass complex mathematics, later validating their work with precise electromagnetic simulators. By strategically placing the resistors at the loop terminals and assuming they do not interact with the coil's magnetic field, we can model the loop as a single-turn inductor and use KVL and KCL outside the inductor. This clever shortcut lets us analyze the system using circuit theory rather than solving Maxwell equations. While it does not perfectly mirror physical reality, it provides the essential insights needed to kickstart a design. I think the key difference between this configuration and Walter Lewin's configuration is the location of the resistors relative to the changing magnetic flux. In the configuration shown here, the resistors are connected at the terminals of the loop. If we assume that the magnetic field is confined to the loop itself and does not interact with the resistors, then a loop can be modeled as a single-turn inductor with external resistors connected across its terminals. Under this assumption, the electric field in the resistor region is conservative, so circuit theory and KVL can be applied there, where the voltage across the loop is L dt, where L is the inductance of the loop. Now, why is the voltage across the loop equal to L dt? Starting from Faraday's law, the line integral of E all the way around any closed path is equal to the negative of the rate of change of the magnetic flux through the loop. Consider a closed path that starts at terminal A, travels through the loop to terminal B, and then returns from B to A through the space outside the loop. Inside a perfect conductor, the electric field is zero or perpendicular to the path along the loop. Therefore, the contribution to the line integral along the conductor is zero. The entire contribution comes from the path outside the inductor. Since we have assumed that the magnetic field is confined to the interior of the loop and is absent in the external region, the electric field outside is conservative. As a result, the integral from B to A is path independent, allowing us to define the potential difference between the terminals. This potential difference is what we call the voltage across the inductor. Therefore, V is equal to N d phi dt, where N is 1 as the loop forms a single-turn inductor. d phi dt is equal to d phi di times di dt. Now, N di dt is what we call the inductance, so the voltage across the inductor is L di dt.
So you see that the voltage across both R1 and R2 is equal to the voltage across R1 plus the voltage across R2, which is the same voltage across the loop. This shows that the voltage across the loop is not zero, unlike what we thought, but is equal to VR1 plus VR2. The loop is the secondary of a transformer, with the primary being my coil. Dr. Levin's model misses a transformer in the loop, with the voltage across the winding equal to VR1 plus VR2. KVL holds.
This derivation relies on the existence of external region, where the electric field is conservative and terminal voltages can be defined, which is an assumption for simplification. In Walter Lewin's configuration, however, the resistors lie inside the loop that encloses the changing magnetic flux. The induced non-conservative electric field acts directly along the resistors themselves. In that case, there is no way to separate the circuit into a magnetic region and an ordinary circuit region, where a scalar potential can be consistently defined. Consequently, the usual form of KVL does not apply. So while the lumped element model is valid when the magnetic field is confined to the inductor and the rest of the circuit is outside the flux region, it is not directly applicable to Lewin's setup, where the changing magnetic field interacts with the resistors. So this is not equivalent to Dr. Lewin experiment. He then introduced what he referred to as the extreme case. In this scenario, he removed the resistors from the loop, leaving a simple loop with a small gap. This configuration essentially forms a typical single-turn inductor. As we discussed earlier, in such a loop, made of a very good conductor, the line integral of the electric field along the conductor itself is zero. The time-varying magnetic field enclosed by the loop induces an electric field, but only across the gap between the inductor terminals.
Now if we measure the voltage across this tiny gap on this side,
When he measured the voltage across these two terminals at the gap, he observed the voltage poles. However, when he measured the voltage between the same two terminals along the conducting path of the loop, he obtained 0 volts.
Here I have the same loop with the sense lines running right on top of the loop, and we have no voltage jump, just some noise.
This difference arises because the loop is made of a highly conductive material. In an ideal conductor, any internal electric field would induce an infinite current, which is non-physical. Therefore, the electric field inside the conductor must be 0. And the entire induced voltage appears across the external gap, through the air. Because the magnetic field is time varying, the induced electric field is non-conservative, as we previously noted. This means the voltage becomes path dependent. If you measure the potential difference between 2 points along one path, you might get one value. Measure along a different path, and you could get a very different result. However, his interpretation of this situation was quite strange, and I found myself unable to agree with it.
So if in fact we have a voltage V across this gap, for reference say 0 volt here and plus V on this side, why do we read 0 volt across the sense lines? Let's take halfway through the loop. If the voltage here is plus V, the voltage here would be half a V. So we have half a V across this half of the loop and another half a V across the other half. There is no current running through the sense lines, so it doesn't matter that they are going to the scope. Both the sense lines and the loop have the same shape and are in the same field, so they behave the same. Which means we have half a V on this sense line and another half a V on the other sense line. So if the voltage of the loop on this terminal is V, it is reduced on the sense line by half a V here, and on the 0 terminal it is increased by half a V here. So you see that the voltage difference between the sense lines is 0 at this point and the scope shows 0.
He claimed that there is an induced voltage across the loop wire. However, loop wires are made of good conductors, and if we assume their resistance to be negligible, there should be no electric field along the wire, hence no voltage drop across it. This claim seems inconsistent with what he stated at the beginning of the video, and it also contradicts the analysis he referenced from Romer's paper in his second video. For these reasons, I disagree with his claim.
So the entire reason Dr. Lewin was reading two different voltages was due to bad probing. No matter where you cut your circuit, the voltage...
He then concluded that Walter Lewin measured two different voltages across the same 2 points due to bad probing. However, he himself performed the same experiment and obtained the same result: 2 different voltages across the same 2 points. Despite this, he did not demonstrate that he could measure the same voltage across those points using a different probing path. Instead, he tried to justify his unusual claim with what I believe to be a questionable and unconvincing analysis.
If you look at this half of the circuit, the voltage across this half is V1, which is the voltage across this piece of loop wire, plus the resistor voltage, which is VR1, plus V2 of this piece of wire. Now if you sense it like this, the same voltages of the loop wires are induced on the sense lines, which subtract from the voltage across these points, and all you read at the scope is VR1. And if you sense on the other side, the induced voltages on the sense lines change to match that side, and you read VR2.
To further challenge this reasoning, let's assume the 2 resistors in the loop are identical. Based on the experiment's reported results, one would read plus 4 volts across R1 and minus 4 volts across R2. If V1 and V2 are each 1 volt, then the total voltage between points A and B in the left branch would be 6 volts. To match that same 6 volts in the right branch, while accounting for the minus 4 volts drop across R2, V3 and V4 would have to sum to 10 volts. Assuming V3 equals V4, each would have to be 5 volts. But then the question arises, why are V3 and V4 5 times larger than V1 and V2? What physical principle or parameter determined this scaling? There seems to be no scientific basis for such a discrepancy. This analysis not only lacks theoretical justification, but also contradicts the analysis he referenced from Romer's paper in his second video, in which it was clearly stated that there is no voltage drop along the loop's conducting wires.
No matter where you cut your circuit, the voltage across these 2 points is always a unique number. The voltage on this half of the circuit is the same as the other half. There were never 2 different voltages across these points. This emphasizes the importance of proper probing.
If there's a well-defined voltage between points A and B, then there should be no circulating current. I believe he agrees that a circulating current exists in the loop. But if that is the case, then the voltage between points A and B must be different depending on the path taken. For a counterclockwise current to exist, the voltage between points A and B in the left branch must be positive, while on the right branch it must be negative. This contradicts the assumption of a single well-defined voltage between those 2 points. Furthermore, this analysis assumes a voltage drop across ideal conducting wires, which goes against basic principles of electromagnetism. Good conductors should have negligible resistance, and, therefore, no significant voltage drop along their length.
Now I'm not 100% sure, but if my quick analysis is correct,
Finally, he proposed a new method of probing the circuit to obtain consistent voltage readings across the same 2 points. However, he never tested or demonstrated this technique to show that it actually results in consistent voltage measurements regardless of the probing path. He also acknowledged that he is not entirely certain about this approach, which I appreciate as it shows openness to further investigation.
My conclusion? Kirchhoff laws hold and have held nicely for me so far. If you see any discrepancy, it's because you're either missing a component in your model or probing wrong.
In conclusion, I find ElectroBOOM analysis inconsistent, unsupported by standard electromagnetic theory, and contradictory to the results and references he cited in his second video.
Voltage is basically defined as the amount of potential energy.
In the second video, he begins by introducing some fundamental concepts such as voltage, electric forces, and Kirchhoff's voltage law. However, a significant issue arises in his explanation of electric forces and electric field. His definitions appear to be limited to conservative electric fields, specifically static electric fields, as found in electrostatics.
It is like gravity. It doesn't matter if you move sideways because the gravity always points down. The mass will lose its potential energy as it gets closer to the Earth and will gain the same amount back when you return to the same point.
This is problematic because the context of our experiment involves a time-varying magnetic field, which in turn induces a time-varying rotational electric field. In other words, we are dealing with electrodynamics, not electrostatics. In such scenarios, the induced electric field is non-conservative, meaning that the work done by the field depends on the path taken, and its curl is non-zero. Therefore, restricting the definitions to conservative electric fields fails to accurately represent the physical nature of the experiment. It's important to distinguish between electrostatic and electrodynamic fields to avoid conceptual misunderstandings, especially when discussing phenomena involving electromagnetic induction. Although I've touched on this in previous sections, it's worth taking a moment to clearly differentiate between conservative and non-conservative fields. Conservative fields or forces are those in which mechanical energy is conserved. This means that the sum of kinetic energy and potential energy remains constant throughout the motion. In other words, the change in kinetic energy plus the change in potential energy is zero. For example, in a conservative electric field, if we move a charged particle through some distance against that field or force, the work done on the particle increases its kinetic energy. For the total mechanical energy to remain conserved, this increase in kinetic energy must be matched by an equal decrease in potential energy, so that the sum of the changes in kinetic energy and potential energy is zero. Now, imagine the charged particle moves in a closed loop, ending up at its original position. Since potential energy is a function of position only, and the position is unchanged, the change in potential energy must be zero. That also means the change in kinetic energy must be zero, and therefore, the total work done by the field in a closed loop is zero. This is a defining characteristic of conservative fields. In a conservative field, the total work done around any closed path is zero. But what if the work done on a charge around a closed loop isn't zero? In that case, the field is non-conservative, and it is not possible to define the unique scalar potential energy for it. Why? Because if a scalar potential did exist, then returning to the same position should always bring the system back to the same energy state. If a test charge gains or loses energy after completing a closed loop, it would imply that the same position has different energy values. This contradicts the very idea of potential energy as a single-valued function of position. So, is something wrong with the equation delta KE plus delta PE is 0 in such a case? Yes, in a non-conservative field, mechanical energy is not conserved. The field does work in a particle in such a way that the total kinetic energy and potential energy can increase or decrease. That's what defines a non-conservative field or force. One important example of a non-conservative field is a dynamic electric field, such as the one induced by a changing magnetic field. In such cases, net work is done on a charge moving through a closed loop. This means energy is being added to the system, for example, to drive current in a wire, but this energy isn't coming from nowhere. It's coming from the energy stored in the changing magnetic field. So while mechanical energy, kinetic plus potential, isn't conserved just by the electric field, the total energy of the full electromagnetic system, including the magnetic field, is still conserved. This is an important point. The system doesn't break the laws of energy conservation. The energy is simply transferred from the magnetic field into the motion of charges. If the electric field lines form closed loops, then a charge following that path will continuously gain or lose energy, meaning the field cannot be conservative. This makes it impossible to define a scalar potential alone. This difference between static conservative fields and dynamic non-conservative fields is captured beautifully in Faraday's law of induction. This equation shows us that the curl of the electric field is directly related to how fast the magnetic field is changing with time. If the magnetic field is not changing with time, partial B partial T is 0, then the curl of E is 0. In this case, electric field is 0, and we can write E equals negative grad V, where V is a scalar potential. But if the magnetic field does change with time, then the curl of E is not equal to 0. This makes the electric field non-conservative, and it can no longer be described solely by a scalar potential. This ties back to a key result in vector calculus. A vector field E can only be written as the gradient of a scalar function if and only if its curl is 0. If the curl isn't 0, then a scalar potential by itself isn't enough. This leads to a deeper insight. In dynamic electric fields, like those caused by changing magnetic fields, we must go beyond scalar potential. In such cases, the electric field is described as E equals minus grad V minus partial A partial T. Here A is the vector potential. So to fully describe the electric field in time-varying situations, we need both the scalar potential V and the vector potential A. So ultimately, the key difference between static and dynamic electric fields lies in how they behave mathematically and physically. Static fields have zero curl and can be described by scalar potential, conservative. Dynamic fields have non-zero curl and need both scalar and vector potentials to be properly described, non-conservative. So Kirchhoff's voltage law is based on the conservation of mechanical energy and applies only in conservative fields, where the work done on a charge equals the change in its potential energy. Since no energy is added or lost in such systems, the net work around a closed loop is 0, implying 0 net potential difference. However, in non-conservative fields, such as those in electrodynamics, Faraday's law shows that the work done around a closed loop is not 0 due to time-varying magnetic fields. In this case, mechanical energy is not conserved, but total energy is. As work done on moving charges and generating currents goes into generating magnetic fields, or magnetic, which will induce electric field, and so on. In general, electromagnetic energy alone is not conserved, nor is the mechanical energy of the charges. This is expected because the electromagnetic fields do work on the charges, and the charges in turn generate fields. Energy is continuously exchanged between the fields and the matter. Therefore, to properly account for energy conservation, one must consider the combined contributions of both the fields and the charged particles. So, KVL applies only in electrostatics, and basically says that the closed-loop integral of E to dl is 0, or that the curl of the electric field is 0. That's what KVL is. However, he holds a different opinion in this, which I completely disagree with.
But that's not the definition of KVL. KVL says that the sum of all voltages in a loop must be zero. But then you might say that the voltage is integral of EDL. But that's not true. Voltage is any energy per unit charge, not just energy from electric sources.
The idea that voltage is simply any energy per unit charge is something I would respectfully disagree with. Voltage is the potential difference between 2 points, which is directly related to the difference in potential energies between those locations. However, potential energy is only defined in conservative fields. In such fields, mechanical energy is conserved, and the work done on a charge moving from point A to point B is equal to the difference in its potential energy between those 2 points.
Is that it? Does Dr. Lewin believe that voltage is only defined by electric forces? It seems he doesn't think of d phi over dt as a different entity. He thinks that minus d phi over dt is only the value of this integral and is not a separate entity. But that's not true. These two are two different entities that exist in a circuit with their values equal in a closed loop.
I agree with Walter Lewin, and I respectfully disagree with the assertion that the partial derivative of phi with respect to t is a separate entity. Rather, the integral in the left-hand side of Faraday's law represents the curl of the induced electric field, while the partial derivative of phi with respect to t is the value of that curl. The curl is a vector operator that quantifies the rotational tendency of a vector field. To visualize this intuitively, imagine placing a tiny paddle wheel in a fluid flow. If the field causes the paddle wheel to spin, this indicates a non-zero curl at that point, a vortex-like behavior. The direction of the curl vector shows the axis of rotation, and its magnitude reflects the rotational strength. Conversely, if the paddle wheel doesn't rotate, the curl is zero, indicating an irrotational or curl-free field, where field lines flow smoothly without any inherent swirling. In the case of a time-varying magnetic field, the curl of the electric field becomes directly tied to its change over time, as expressed by Faraday's law in differential form. This equation reveals that a changing magnetic field induces an electric field with a rotational nature. The curl of the electric field is proportional to the negative rate of change of the magnetic field. This rotational behavior is not just a mathematical abstraction, but has tangible physical consequences. It leads to a non-conservative electric field. In such a dynamic scenario, the electric field performs net work on a charge completing a closed loop. This continuous work implies energy input into the system, that is, to sustain an induced current, and the source of this energy is the changing magnetic field. Importantly, energy is not being created from nothing. Instead, it is being converted from the energy stored in the magnetic field. This maintains total energy conservation in the broader electromagnetic system. Even though mechanical energy alone, kinetic plus potential, may not be conserved in the presence of a dynamic electric field. Moreover, dynamic electric field lines always form closed loops in free space and never originate or terminate on charges. This contrasts starkly with static electric field lines, which begin and end on electric charges. The closed loops of the dynamic field lines show that the field has a rotational nature, which agrees with the idea of non-zero curl. So in a dynamic, non-conservative electric field, a charge moving around a closed loop can gain energy because the field continues to do work on it, continuously driving the charge and transferring energy to it.
It seems he doesn't think of d phi over dt as a different entity. He thinks that minus d phi over dt is only the value of this integral and is not a separate entity. But that's not true. These two are two different entities that exist in a circuit with their values equal in a closed loop.
Yes, a magnetic field may coexist in a circuit alongside with the induced electric field, but it does not do any work on the charges. A magnetic field does no work on a charged particle because the magnetic force it exerts is always perpendicular to the particle's velocity. Work is defined as the component of a force in the direction of an object's displacement multiplied by the magnitude of that displacement. Since the magnetic force is always perpendicular to the direction of motion, it has no component along the direction of displacement. As a result, the magnetic force does no work on the particle. A time-varying magnetic field induces a circulating electric field, as described by Faraday's law of electromagnetic induction. This induced electric field does work on the free charges in a conducting loop, causing them to accelerate and generate an electric current. Importantly, the magnetic field itself does not directly do work on the charges, since the magnetic force is always perpendicular to the velocity of a moving charge, and therefore does no work. Instead, energy is transferred through the induced electric field, which performs work on the charges. As the current flows, it produces its own magnetic field that opposes the change in the original magnetic flux, in accordance with Lenz's law. This ensures conservation of energy. The electromagnetic field transfers energy to the moving charges, giving them kinetic energy and creating electrical energy, and the system resists changes through the generation of opposing fields. In summary, the energy dynamics involve conversion between the field energy and mechanical energy, with no violation of energy conservation. The magnetic field induces an electric field. The electric field does work on the charges, and the resulting current generates opposing fields, maintaining balance in the system. He then adopted Romer's analysis, which contradicts his own explanation in his first video, where he claimed that there is an induced voltage in the loop wire. I briefly mentioned the lumped element model in a previous section, but I'll be diving deeper into the lumped matter discipline in a separate, more detailed discussion. For now, let's quickly revisit the key assumptions of the lumped element model. In order to define voltages between any 2 points in a circuit and currents through the wires, each segment of the circuit must satisfy a few important constraints, essentially the same ones imposed on each lumped element. 1. No time-varying magnetic flux should link with any portion of the circuit. That is, the partial derivative of phi with respect to t must be 0 for all time. 2. No net charge accumulation at any node, meaning the rate of change of Q with respect to time must be 0 at every node, where a node is any point where 2 or more element terminals meet. 3. Signal timescales must be much larger than the electromagnetic wave propagation delays across the circuit. In the case he's analyzing, the first 2 conditions are not satisfied. There is a changing magnetic field enclosed by the circuit, which induces an EMF per Faraday's law, so KVL does not strictly hold. The loop integral of E dot dl is non-zero. Additionally, there is charge accumulation at resistor boundaries, which violates KCL as we saw previously. He didn't mention the rise time of the step input, but assuming it's similar to Walter Lewin's experiment, 10 milliseconds, the highest frequency component would be approximately 35 Hz. That corresponds to a wavelength of about 8,570 kilometers, which is vastly larger than both the dimensions of his components and the overall circuit. So the third condition is indeed satisfied, and the transmission line effects can still be neglected in this regard. I've read chapter 22 of Feynman Lectures in Physics, Volume 2, particularly the section discussing the circuit he mentioned. Dr. Feynman indeed states that the sum of the voltage drops around any closed loop in a circuit is 0. That's the standard form of KVL. But there's a really important assumption he makes to get that result. Let me quote directly. According to our approximations, there is no magnetic field in the region outside the individual circuit elements. Therefore, the line integral of E around any curve which does not pass through any of the elements is 0. That assumption is crucial. He's effectively saying that the circuit is not linked by any time-varying magnetic field. Without that, Faraday's law doesn't come into play, and KVL holds just fine. But in an ElectroBOOM circuit, that condition doesn't apply. He clearly has a changing magnetic field outside the elements, and that magnetic field links the circuit elements and penetrates the loop. That violates the assumption Feynman made in his derivation. So in this case, KVL doesn't strictly hold. Instead, we need to use Faraday's law. This tells us that the sum of voltage drops around the loop is not 0. It's equal to the negative rate of change of magnetic flux through the loop. It's a subtle but important distinction, because when time-varying magnetic fields are involved, the lumped element assumptions break down, and we have to be more careful applying KVL and KCL. So neither the lumped element model nor KVL or KCL hold in that experiment. In section 11 of his document, titled KVL, Dr. Belcher said, "Many introductory texts on electromagnetism are not precise about what exactly they mean by the voltage drop across the inductor, and many students come to incorrect conclusions about what this actually means. The most common misconception is that the minus L dt voltage, read by the voltmeter just above, represents the integral of E dot dl through the inductor. But if the inductor wires are perfectly conducting, this integral is zero because there is no electric field in the wires. One textbook that makes perfectly clear what the voltage across the inductor is the textbook by Feynman, Leighton, and Sands, the Feynman Lectures in Physics, Volume 2. In that textbook, the authors state explicitly that the integral of E dot dl through the inductor must be zero, and they define the voltage difference across the inductor as the closed-loop integral of E dot dl, which by Faraday's law is minus L di dt. But this quantity, which has units of volts, has nothing to do with the integral of E dot dl through the inductor, which is zero. Thus, with Feynman definition, the sum of all voltage differences around the circuit is zero. That is, KVL holds.
V minus IR minus Q over C minus L di dt equals 0. But the first three terms here are the integral of E dot dl through the various circuit elements, and the last term has nothing to do with the integral of E dot dl through the inductor, which is 0. In this sense, KVL holds as argued by Mehdi Sadeghdar, but one must always remember that the voltage difference across the inductor is defined in a very different way compared to the voltage difference across the other three elements. Based on the context, I believe Belcher is referring to the series RLC circuit that was introduced by Walter Lewin in his analysis aimed at showing that KVL doesn't always hold.
What are you saying? It's zero! Exactly because there is no resistance. So E here is zero. So the integral E dot dl through this wire is zero.
If Belcher is referring to that same RLC circuit, then I agree with him that KVL does hold in that specific case, as the circuit consists of lumped elements, and there is no time-varying magnetic field either crossing the circuit or present outside the elements. However, I don't fully agree with all of his statements. I'd like to comment on this line where he says, "But the first three terms here are the integral of E dot dl through the various circuit elements, and the last term has nothing to do with the integral of E dot dl through the inductor, which is zero." Here Belcher refers to Feynman's statement that the line integral of E around any closed curve which does not pass through any of the elements is zero. But by does not pass through any of the elements, Feynman means that the integration path avoids all circuit components, the resistor, capacitor, and inductor, not just the inductor. He illustrated this by drawing a dotted line representing a closed loop that bypasses the circuit elements.
So a current is going to run in this direction, through the resistor, in this direction, through the self-inductance, in this direction.
This is where the misconception appears in Walter Lewin's explanation. To be clear, I completely agree with Dr. Lewin that KVL does not hold in the presence of non-conservative electric fields, such as in the experiment he presented in Lecture 16. In that case, the electric field is induced by a changing magnetic flux linking the entire loop, so the line integral of E around the loop is not zero, and the conventional form of KVL breaks down. However, I disagree with his explanation in this RLC circuit. Consider a series RLC circuit. Circuit theory tells us that the voltage across the resistor plus the voltage across the capacitor plus the voltage across the inductor is zero, where the inductor voltage is L di dt. Dr. Lewin instead argues that the voltage across the inductor is zero, and the sum of the resistor and capacitor voltages equals d phi dt.
That is E dot dl over the capacitor. Now I come to the self-inductor. The integral E dot dl between this point and this point is 0. So according to Faraday's law, that is minus di dt, for which Jason will tell you that that is the same as minus L di dt. Now look at this equation now. This is the closed loop integral of E dot dl. Then according to Kirchhoff would have to be 0, but it isn't. It is minus L di dt.
Going as far as saying that textbooks are wrong in their treatment of the circuit.
Now I'll tell you that almost all college physics books cheat. They do it wrong, but they get the right answer. Why do they get the right answer? Because they know the answer. They write the following. So this is the honest way it should be written, according to Faraday's law. And this part is the closed loop integral of E dot dl. The college physics books, most of them are written by physics teachers who do not understand physics. They write it this way. And then they say, do you know why this is 0? Because of Kirchhoff. They say, look, this is the closed loop integral of E dot dl, and that has to be 0 according to Kirchhoff. This is not only wrong, but as I said earlier, it is criminal, because this is not the closed loop integral of E dot dl. This is the closed loop integral of E dot dl, and that is not 0.
I don't think that conclusion is correct, because it mixes the field description with the lumped element model. In circuit theory, the magnetic field produced by an ideal inductor is assumed to be confined to the inductor itself and does not significantly interact with the rest of the circuit. The inductor is treated as two-terminal black box whose terminal voltage is defined as L di dt. With that assumption, if we draw a closed path that does not pass through the interior of any circuit element, the electric field along that path is conservative and there is no changing magnetic field penetrating it. So the line integral around the path is 0. The result is exactly the familiar KVL equation, VR plus VC plus VL is 0. In fact, Dr. Walter himself acknowledges this point. When he connects a voltmeter across the inductor, he says the meter reads L di dt, not 0.
And I'm going to attach here a voltmeter. What will this voltmeter show? And you will probably say, well, didn't you say that integral E dot dl through the wires here is 0? So you would think that V here is 0, but that's not true. You know what that V is going to be? It's going to be plus L di dt. In other words, this equation is now correct. And you will say, now what happened now with your phi dt? Well, what I have done in a clever way, by going around the circuit, I have now no longer any change in magnetic fluxes going through my open surface, which is now attached to my new closed loop. And my new closed loop following is like this. And look, when I come here, I bypass that self-inductance, I go through the voltmeter, and I come here, and I come here. And so now, Kirchhoff's loop rule should hold, and so the sum should be 0. Therefore, it shouldn't surprise you that this plus L di dt is exactly what this voltmeter then will show.
Likewise, when he chooses a loop that bypasses the inductor, he concludes that KVL works.
Now when you arrive here, you leave the circuit, and you go this way. You can choose your path, I don't care. And you come back to the circuit here. But while you are going this dotted line, which could be just through the air like this, you measure the integral of E dot dl over that path that you have chosen. And what will that integral show? Plus L di dt. Again, you have now chosen a loop whereby there is no longer any changing magnetic flux going through that surface. And so Kirchhoff's loop rule works.
That is entirely consistent with the lumped element model. The key point is that KVL is valid here because the magnetic flux is confined within the inductor and does not link the entire circuit loop. That confinement is one of the assumptions behind lumped element circuit theory. A similar situation already exists with a capacitor in the same circuit. If we zoom in physically, there is no conduction current passing through the dielectric. The capacitor is literally an open circuit. Inside it, the changing electric field gives rise to displacement current, not conduction current. Conduction current flows into one terminal of the capacitor, Across the dielectric, it is represented by displacement current, and at the opposite terminal, it becomes conduction current again, allowing current continuity throughout the circuit. At the first node, a conduction current I enters the node, while no conduction current leaves it. At the second node, no conduction current enters the node, while a conduction current I leaves it. Does that KCL fails? Of course not. Within the lumped element model, the capacitor is treated as a black box with two terminals. Whatever the microscopic physics occurs inside, whether conduction current becomes displacement current and then becomes conduction current again, is irrelevant to circuit equations. The only quantities that matter are the terminal voltage and terminal current. The current entering one terminal is equal to the current leaving the other, so KCL remains perfectly valid. So if we treat the capacitor as a node, the current entering is equal to the current leaving it. The same reasoning applies to the inductor. The lumped element model does not require us to describe the detailed electromagnetic processes inside the component every time we analyze a circuit. It simply assigns the inductor a terminal voltage of LdI/dt, regardless of the internal field distribution. As long as the magnetic field remains localized within the inductor, as assumed by the lumped element approximation, the standard KVL equation remains valid. VR plus VC plus VL is equal to 0. Now, according to Mahdi's understanding, Belcher's reference to Feynman implies that Feynman's definition of voltage aligns with Mahdi's own and that KVL holds in all cases.
So Professor Belcher also concluded that Dr. Feynman himself and I have the same definition for voltage and the KVL holds in all cases.
If that interpretation is correct, then I respectfully disagree with Belcher. Feynman's actual position is that voltage is defined only in conservative electric fields. This means KVL holds only when the circuit can be accurately approximated using the lumped element model and when no time-varying magnetic field exists in the space enclosed by the circuit. The voltage, or potential difference, between 2 points across an electrical element is defined as the work required to move a unit positive charge from one point to the other against the electric field along any path. For this definition to be valid, the voltage between 2 points must be unique and independent of the path taken. This condition is satisfied when the electric field is conservative, which implies that the circulation of the electric field around any closed loop is zero. This requires that there is no time-varying magnetic flux linking the circuit elements from the outside. If such a varying magnetic field is present, Faraday's law indicates that an induced EMF will be generated, leading to a non-conservative electric field. In such cases, the concept of a scalar electric potential, or the voltage, becomes ill-defined, and the voltage between 2 points becomes path-dependent. Therefore, KVL, which states that the sum of the voltage drops around any closed loop in a circuit is zero, holds true only under the assumption of the lumped element model. This model assumes that all electromagnetic effects are confined within the elements, and no time-varying magnetic field link the circuit externally. In conclusion, Kirchhoff's voltage and current laws hold only when two conditions are satisfied. First, the circuit must follow the lumped element abstraction. Second, there must be no time-varying magnetic flux linking the loop externally. If these conditions are not met, KVL and KCL do not strictly hold.
Even if the fields are not contained and leak outside, we still have an inductor and defined voltages everywhere and KVL holds.
I disagree with this point, because if the magnetic field generated by an inductor is not fully confined within the component and instead leaks into the surrounding space, it can influence other parts of the circuit. This leakage introduces a non-conservative electric field due to the time-varying magnetic flux. As we previously discussed, a non-conservative electric field does not have a well-defined scalar potential function, meaning the voltage between nodes is no longer uniquely defined. This violates one of the fundamental assumptions of the lumped element model, which requires that any time-varying magnetic field must be completely contained within the individual circuit elements and must not extend into the space between them. If the magnetic field leaks outside the inductor, the concept of node voltage becomes ill-defined. As a result, KVL no longer holds, since KVL assumes that the electric field in the circuit is conservative and that a unique voltage difference exists between any 2 points.
One of the examples people brought to disprove my conclusions was that what if the entire loop was made of a uniform resistive element, and we take these 2 points and the induced current I would create 2 different voltages across the same points based on Ohm's law. What you must understand is that a real resistor is only ideal if it's infinitely small. As soon as it has any dimensions, it at least has an inductance series with it, especially something this long.
I disagree. The lumped element model assumes that the component electrical properties, resistance, capacitance, and inductance, are concentrated at a single point in space. A quick rule of thumb is the 1/20th wavelength rule. If the circuit is smaller than 1/20th of the wavelength, the lumped element model is valid. Let's assume that the rise time of the step signal is 10 milliseconds. As we discussed earlier, this gives us a highest frequency component of about 35 Hz. That corresponds to a wavelength of roughly 8,570 kilometers. Now suppose the circuit has a radius of 10 centimeters. That means the total parameter, the length around the loop, is about 62.8 centimeters. Now compare that to 1/20th of the signal's wavelength, which is about 428.5 kilometers. The circuit is extremely small in comparison. In fact, 62 centimeters is tiny compared to 428 kilometers. So the lumped element model works perfectly here. We can treat the resistor as if all its properties are concentrated at a single point. This simplification holds true as long as we assume the changing magnetic field enclosed by the circuit is negligible, and no charge accumulation at any node.
Remember, to make it easy, you have to produce a model using lump elements. You pull out the resistance and the secondary inductance and put them in series for each half of the circuit. If you assume a uniform field through the loop and D1 and D2 are the length of each side, this is what you get, and a known voltage across these points, and KVL holds.
You agree that the current flowing in a circuit is rotational. This means that the current circulates around the loop, rather than flowing directly from one point to another through multiple paths simultaneously. For this rotational current to exist, the voltage between points A and B must differ depending on the path taken, positive along the left path and negative along the right path. If the voltage between points A and B were the same and path independent, the current would flow from A to B through both paths equally, eliminating the possibility of a circulating current. Rotating current means a current that starts at a point and returns to the same point, forming a complete cycle. For instance, this current is not circulating. Although it moves around a circular loop, it starts at the positive terminal of the source and ends at the negative terminal, so it does not return to the same point, and the cycle is not complete.